Oh. It's a bad application. All right, let's get started. This is our third lecture, and we have a lot to cover. Shall we go quickly? Yes? How are we going so far? Is it fast, quick, slow? Just right? Okay. We'll try to keep that pace then. Okay, we'll cover ISA trade-offs today, but this is where we left off last time. I didn't cover this. You read about design point, right? In the article that you're supposed to read. Basically, design point, any processor is really designed for a design point. This is basically the set of design considerations and their importance. And this actually leads to trade-offs in both the ISA and the microarchitecture whenever you're designing a processor. Is it locked?
Yeah, it was locked.
No. I don't know how to fix that, but I guess let's keep it this way. Any processor that you're designing has this design point, and there are many considerations. Basically, design point really determines those considerations. Cost, performance, power consumption, energy consumption, availability, reliability, correctness, time to market. And this design point, all of these considerations are actually determined by the problem space or the application space that you're designing the processor for, or the intended users and the market. If you're designing a general purpose processor like Intel does, actually pretty much all of these are considerations because you're catering to so many applications that you're trying to find a trade-off that works well for the average application, if you will. It's a tough thing to do to design a general purpose processor because your processor should work for the mobile phone really well, and your processor should work for the server really well too, right? Well, it's become really tough to design processors that work really well for both kinds of applications today. So even general purpose processors are being more specialized to different markets today. For example, if you look at Intel's processors, they have processors that are more or less specialized for the cell phones, right? So it's really your intended application that determines all of these trade-offs. And all of these are actually trade-offs. Like even correctness is a trade-off today, right? And your cell phones actually make that trade-off. If your battery is running low, for example, you can actually sacrifice some image quality if you're watching a video. Right? Maybe you can get rid of some pixels and don't display some of the pixels. Maybe you can approximate, right? This trade-off is actually made over the internet. It's not on the processor design. But when you're sending data over the internet, streaming video, you may decide to stream a version that's compressed in a lossy fashion. Right? That way you save a lot of bandwidth. Right? So you lose correctness, some sort of correctness, because it's not the perfect image that was recorded or perfect video that was recorded. But it may be OK because the user can tolerate it, right? Especially if your battery is running low. So you can make decisions like that in the correctness domain as well today. And this is interesting because now you can trade off potentially energy consumption and correctness. You can save energy but be less correct. And this is an interesting direction going forward. Traditionally, general purpose processors have been optimized for performance and cost. But going forward, actually today, all of these are important concerns. And we'll cover some of these as we go along in this course. Keep this broad view in mind. How does a design decision affect performance? A lot of the focus will be on performance. And traditionally, a lot of the focus has been on performance. But the design decisions that you make affect all of these. And one of the things that determines cost is especially time to market. Right? Time to market is affected by how long it takes to design the processor and how long it takes to verify the processor. Right? You can actually trade off correctness and time to market too in your design point. What can you do? For example, you can decide to market your processor early without testing it a lot. Right? Is this a good idea? Well, maybe. It depends on what you do, right? If you don't have any way to fix the problem, maybe it's a bad idea, right? Maybe you've sent out a lot of buggy processors. But if you have a way to update your processor while it's in the field, if you can patch some of the hardware bugs, and if people can apply that, of course, then maybe it may be an interesting idea to actually market your processor early without fully testing it. And as you test it, as you figure out the bugs, patch it. Of course, the bugs shouldn't be really critical, right, in this case. But then you can shave off some time to market, shave off some cost, And you can guarantee correctness over time, right? Hopefully. Guarantee is a tough thing to do because even the processors that have been in market today for a long time have bugs. Any of you looked at the errata sheets of processors? There are lots of errors actually in the processors that you're using. If you look at the errata sheet, if you search for the errata sheet for Intel processors, you'll see that there are a bunch of errors. And usually these errors come from the new features that are added to the processor that have not been tested over time for a long time. Now, it's not clear how often these errors, hardware errors, are actually encountered in real life, and how often do they affect correctness of the programs. That remains to be seen. But this happens even after extensive testing today. Yes?
When you mentioned sacrificing correctness for maybe like something like energy consumption, increasing the battery life, I know you mentioned a network, but is there any actually like chip level things of correctness? Like, is there some kind of architecture where you can maybe make the FPU like have precision or something?
That's right. Yeah, there are actually architectures that do that. There are some chips where you can make the FPU have precision, especially for physics acceleration. People have proposed that. In general purpose processors, I mean, software can always make that trade-off, right? But in hardware, that trade-off is not made today, as far as I know. But that has been done a lot in software for a long time, in supercomputers too. Okay? Actually, lossy compression is one example, right? You could do that in hardware or software too. Anyway, but keep this in mind, basically. Any design decision that we make will affect a lot of these things. And maybe I have some things that are not here, right? Maybe you can imagine those. So application space actually determines the design point, and application space is huge. Right? If you're designing a processor for a specific application, then these trade-offs are probably easier to make. If you're running only one application in your system, let's say streaming video, then these trade-offs are a lot easier to make, hopefully. Right? Then you're concerned about only what your users want for that particular application. If you're running applications that you do not even know, then how do you make these trade-offs? That's what makes computer architecture an art. And this is actually from the paper you're reading. This is just some applications. And there are many applications, process-based, business data processing. These are all becoming important, even more important. Network applications, real-time applications, embedded applications, media applications. I guess it says random software packages. It's scary, right? You're designing this processor that you have no idea what will run on it. And you should still get good performance, good power characteristics. I think that's the challenge of computer architecture. That's what was exciting to me when I first started in this. You're designing this, and how do you get good performance, right? It's tough. It's not that easy. But hopefully this course will give you some trade-offs to make. OK. What are those trade-offs? Well, in this course, we'll cover all of these different kinds of trade-offs. And this is what I call the soul of computer architecture, really. We'll start with some ISA-level trade-offs today. But there are a bunch of trade-offs at the microarchitecture level. There are a bunch of trade-offs at the system and task level. There are trade-offs at the entire levels of transformation over here. But we'll cover the trade-offs that we make around here. And one of the key questions going forward is how do you divide the labor between hardware and software? And some of the ISA-level trade-offs that we're going to examine today will hopefully cater to that. But there are a lot of system and task level trade-offs that consider this. So you'll see a lot of these trade-offs. So keep this in mind also. And computer architecture is really the science and art of making the appropriate trade-offs to meet a design point. I say science and art. Actually, I should have said just art, perhaps. Science is very tough in this case. Why is it tough? Yeah?
There's no algorithm to arrive at a solution. It's kind of like you have to feel best where you have some idea, but you also have to kind of just make these decisions of where the resources should be allocated towards.
That's right, exactly. There's no model that you can easily build to say that for this given application, this will be my performance. Because you may not even know the application, right? And it's very tough to build that model today. Maybe 1,000 years from now, somebody will come up with that model. But basically, it's art because you do not really know the future, or maybe even the present, right? You do not even know what the applications will run on your processor. Right? That's why it's easier to do this, easier to model things if you're running only one application. If you're very, very application specific, you can make it more of a science. But if you have many applications that are running on your system and you're trying to optimize for some metric, let's say it's even a single metric, performance, even that's tough because you don't know what the characteristics of the application is and you're making that trade-off before you run the applications. Even if you know the applications today, Intel, for example, or AMD or some other company designs processors based on the workloads they see today. Nobody guarantees that that workload will not be different. In fact, the workloads evolve significantly over time, right? And their characteristics change. As a result, you need to somehow anticipate. You need to have this artist's view of the system also, right? I know it's not, it may be tough to swallow initially because we're doing engineering, right? We need to know the results of our decisions, but it's tough to do in this case because you're designing something for the future, right? And that future changes. Okay, and the users will change also. Okay, I guess I said that too. I'll give you an analog from macro architecture too. This is actually true for macro architecture. Also, although it's less so. Who considers macro architecture science? Building architecture, for example. Is that science, you think? Sort of, right? It's the same thing almost, right? It's an art as well. And future is not constant in macro architecture either. This is a loose analogy, but I like this analogy because it ties into something on our campus. For example, can a power plant boiler room be later used as a classroom? Yes? You know one? You studied in one? That thing, right? Yeah. Hammerschlag Hall. It used to be a power plant. In fact, it didn't look like this. I don't know if this is still there. If you read this, at the west end of campus was a small structure that housed a boiler room that functioned as the school's power plant. Below, in the rain beside the railroad tracks, a farmer's goat grazed and occasionally wandered up to eat the grass of this yet untamed end of campus. This is a long time ago. Over a 20-month period between 1912 and 1914, Machinery Hall was built on top of that boiler room. The massive tower, this thing, which has become a symbol of Carnegie Mellon, was designed to disguise the smokestack. So now you know why it exists, that beautiful thing. Architect Henry Hornbostel had created a temple of technology that would become one of the most renowned buildings in the Beaux-Arts style in the country. Beaux-Arts style, right? It's Carnegie Mellon campus is a prime example of the Beaux-Arts style, actually, in the world, almost. And early course catalogs described the boiler room as a classroom where students learned about power generating machinery. The tower continued to belch smoke until 1975. Are you guys as old as that? No? But in 1979, the boiler room became the cleanest room on campus with the construction of the nanofabrication facility. So it's a clean room, actually. The coal bin area became the offices and computer room of the D level. Actually, my research group's lab was actually in that room. Now it's moving because Scott Hall is being built. But basically, macro architecture also changes, and it evolves. Now you could think of this macro architecture as something reconfigurable, right? You can add on top of it, you can destroy it, and you can do something with it. It's harder to do with general purpose processors. But going forward, think about how you can actually adapt a microprocessor to changing future also. This is what is happening in macro architecture. Right? In microarchitecture, in a processor architecture, we might want to do the same things going forward because as applications evolve over time and as we want to keep the processors that we design today, maybe we want a very evolving computer architecture also, self-evolving computer architecture, depending on the application's characteristics. Reconfigurable computing is a very extreme end of it, right? If you can completely reconfigure the hardware such that it can take in the application and generate the circuits, it's an extreme way of doing it. But there are downsides to it also, as we will probably examine, because whenever you run an application, now you need to reconfigure the entire hardware, and that takes a lot of overhead. In fact, the design of the reconfigurable engine has a lot of overhead in itself because it is reconfigurable. Right? It's not specialized. Right? But maybe there's a trade-off space between fully reconfigurable and specialized or fully general purpose. Right? So it's good to think about these things. That's why I like putting this example. It's not a perfect analogy to computers as we have them today, but it's a good analogy showing that It's art and science at the same time. How many of you knew this, by the way? Some. How many of you didn't know it? It's okay. Okay, that's good. Now you know. How many of you have gone to the top of this? Have you seen the smokestack? No? I think it used to be accessible, but not anymore. You might want to check it out. It's a good place. There's an undergraduate lounge over there, right? Or is it the graduate lounge? Graduate lounge? Oh, you don't have access? You can still check it out, and you can tell the graduate students that I asked you to check it out. Say it again.
I've been to the grad lunch. I think it was during UCE day.
Oh, okay. Okay, so it's accessible during UCE day. Okay, next UCE day, remember. But I'm sure if you're curious, you'll find a way of looking at it. Okay, so that was actually the end of last lecture. So let's move on with material for next time. So we're going to cover a lot on ISA and Patterson and Hennessy chapter. These are your required readings. And this actually contains not only the ISA but also the microarchitecture. So this will help. This is a little bit less relevant, but I would still like you to read it. We're doing ARM this time, but this talks about MIPS. But the general principles are really the same. And we will cover LC3B. This is Pat and Patel book. It has a revised Appendix C that talks about the operation of the microarchitecture of the LC3B. And this is LC3 ISA. Actually, we should have an Appendix A, right? Maybe I should change this. Actually, this chapter is still relevant, but I'll also add revised Appendix A. Say it again? Oh, okay, that's good. LC3B ISA. So we're going to cover a bunch of different ISAs, and the more you look at these documents, the better it'll be. I like LC3B because it's simple. MIPS is also relatively simple, but I'll cover a lot of very complex ISAs too. It'll be fun. Okay, let's talk about some ISA principles and trade-offs. There have been many different ISAs over the decades. Not as many as microarchitectures, as we've covered before, and you know the reasons for that. But this is just an incomplete list. x86 is probably the most common and most popular today, right? It's everywhere because it's maintained the software compatibility very well over years. But this is a very old ISA, PDP, Program Data Processor, PDP-11, is being one of the earliest for personal computers, actually. Who knows this one? No one? This was the Digital Equipment Corporation's ISA that allowed them to enter the general purpose PC market. And that was one of the fastest computers of its time, actually. You might want to take a look at it. I'll give you some examples from that. And from that evolved VAX. Who knows VAX? Virtual Address Extensions. That's perhaps the most complicated ISA that has ever been designed. Believe it or not, it's more complicated than x86. And I'll show you some examples. And from that, actually, Digital Equipment Corporation made the choice, perhaps an incorrect choice, in hindsight, to move ISA, this very complicated ISA, to a very simple and nice ISA called the Alpha. And that actually made life really bad for Digital Equipment Corporation, some would argue, because they could have competed with Intel if they continued with the VAX ISA, because they had a lot of software that was written for VAX. But they abandoned all of that software stack and moved to a new ISA. Now, who remembers Digital Equipment Corporation? Only one of you. Okay, two. Who remembers Intel? Well, I don't think I need to ask. But yeah, so that changing the interface, hardware-software interface radically without having provisions to run the existing software can be a very bad decision commercially, right? But you know that from what we've covered earlier, right? But well, we'll get to that a little bit perhaps. But I want to give you that perspective, so I didn't include Alpha here. Well, Alpha is here actually. Okay, there have been a bunch of other ISAs that are interesting. We'll cover some of them. We'll talk about SIMD, single instruction, multiple data. These are very, very different ISAs. SIMD ISA is an ISA that actually, where the instructions operate on multiple data elements. So an instruction can specify 1 million operations, for example. VLIW ISA is similar in the sense that an instruction still specifies multiple operations, but those operations can be totally different. In SIMD ISA, you do add on 1 million elements. In the VLIW ISA, you can do add, multiply, load, store at the same time, all encoded within an instruction. And the instruction guarantees that they actually can be executed in parallel. So these are more parallel ISAs, if you will, multiple operations per instruction. Whereas if you look at x86, it's really single operation per instruction, right? For the data elements, at least. But we'll get to that also. So some other existing ISAs are PowerPC. It still exists. There's a Z ISA, IBM Z. I don't know if it's called Z ISA. It's Z architecture, really, or System Z now. So there's been a variety of ISAs, basically. So what are the fundamental differences between these ISAs? Basically, it's really how they define the hardware-software interface, and that's a huge space, right? For example, how instructions are specified and what they do. How complex are the instructions? These are two of the fundamental differences. We'll cover some of these. But instruction is the basic element of the hardware-software interface, so we should start with instruction. It really consists of an opcode, what the instruction does, and operands, who it is to do it to, basically, on what the instruction operates. This is an example from a beautiful ISA. This is the alpha ISA. It looks nice, right? Nice and clean. I was going to change the labs to alpha because it's so beautiful, but alpha is a dead ISA today. I thought you would be better off learning something like ARM. But you can see that it's nice, right? This is a branch instruction, memory instruction, and operate instructions. And it has a characteristic that we will define later on called uniform decode, meaning the same bits in the instruction specify the same thing across all the instruction formats. For opcode is always at bits 31 to 26. So you can design a nice and beautiful decoder that just looks at those bits and says, this is the instruction, right? So simple. Now we'll see different. This is the ISA that you'll be dealing with. It's a little bit more complex. But it's still not terrible, right? For example, you know that the condition of an instruction is always specified at the top 4 bits. You can decode that relatively easily. You know that for some instruction formats, at least, RM is at the bottom, right? We know that for some instruction formats, the register specifier is here. Although it's not exactly the same register. It's RN versus, I don't remember what's CRN. That's the coprocessor register, right? Yeah. You're not going to implement all of these different instructions, but you might as well start getting familiar with that. This is from the ARM instruction set chapter from the ARM, I guess this is the ARM ISA manual, right? On the website, yes.
I've always seen that, but I've never understood what all the numbers mean.
Which numbers? The top numbers? Or?
Random numbers. Like 332221009.
Oh, this is the bit number. Yeah, it's not very well written, so you need to read it as 31, 30, 29, 28, 27. Yeah, 31st bit. Yeah, it's not the best way of displaying, I agree. So this is bit 0 over here. Okay, good. I'm glad we cleared that. Okay. And this is another ISA. This is also beautiful, I would argue. This is the LC3B ISA. That's why this is a toy ISA. Nobody writes programs for it, but this is a good ISA for instruction, like education. And we'll cover some of these. If you look at this, it's also uniform decode, right? The opcode is always at the top 4 bits. And this is a 16-bit instruction. It's smaller. And if you go over here, actually this is linked from your technical documents from the course website. You'll see the description of the ISA. I forgot to bring a printout of it, but maybe we'll refer to it during the course of this lecture. x86 is another ISA. Actually, I don't have the manual here, but we'll look at it enough times. So there are a couple of things I'd like to point out to begin with. There are many choices that are made when you're designing an ISA, but one of the important choices having these not used instructions. LC3B has it. ARM actually has it. If you look at this, undefined. There's an undefined opcode, if you will, right? Why do you have those? Yes?
For extensions to the language.
That's to the ISA. Well, ISA, you could consider the language also, right? It's language that that's at the boundary of the hardware and software. Yes? Yeah?
Well, extensions to the ISA are also if you have, let's say, like a coprocessor or something.
Mm-hmm.
You only want that to pay attention to that, not have that in the ISA for every other chip. That's part of their part.
That's right. Yeah, this gives basically flexibility to add new instructions or coprocessors as time goes along. And this also gives flexibility to do things under the hood. Maybe you don't want to expose these instructions. Maybe these are hidden commands, right? And if you put this, something happens, right? Something magical happens. It could happen, actually. You just need to figure out how to do that. Okay, so this is usually, the main reason is actually so that you can extend it in the future, add coprocessors, add different instructions. And that has been exploited very well for different ISAs. Some not used instructions became used later on. Not in LC3B, as far as I know. So there's another thing that I want to show over here. For example, if you look at the add instruction over here, it has the destination register. So LC3B has 8 general purpose registers, architectural registers. This is destination register. These bits specify the destination register ID. These bits specify the source register 1 ID. And these bottom bits are opspec. What does that mean? So add, you would expect add takes a source register 1, adds it to source register 2, and places it into the destination register, right? But this add actually does more than that, can do more than that. And what the add does, whether the second operand is a source register 2 or an immediate, is really determined by this A bit. So that A bit says, that A bit describes how to interpret what this operand specification is. This is called a steering bit. It's actually a part of the opcode, if you will, right? You can think of this as 2 different opcodes. Add register to register if A bit is 0, I believe. And if A bit is 1, it's an add register to immediate. But that's called the steering bit. Some people call it the sub-opcode also. Basically, a bit in the instruction determines the interpretation of other bits. You could say the same thing to the opcode, right? Opcode determines the interpretation of the remaining bits. Right? In fact, that's how you interpret. If your opcode is 0001 in this case, you interpret that the next 3 bits are actually the destination register specifier. That's not true if your opcode is 1000, right? It's not destination register. Okay. So a bit this is. I just want to give you that the similar concepts are actually used in different instruction sets. This is bit steering in alpha, for example. Let's see. I have to look at this. So it's actually the same thing. It's an operate instruction. It could be add, just like in LC3D, but actually it could be something else. It could be a subtract. And this bit over here, bit 12, really determines how you interpret the instruction. If bit 12 is 0, then it's a register-to-register operate instruction. You operate on 2 registers and put the result in the destination register. If the bit is 1, you operate on 1 register and 1 immediate, called literal in alpha, and put the result in the destination register. So that concept exists in many ISAs. Okay? Were you guys exposed to this before? Bit steering? Okay. Okay, I'll go quickly then. Who wasn't? Okay. Then I won't go less quickly. Okay, but you know what it is now. You could think of this as a sub-opcode also. Okay, so what are the elements of an ISA? We saw the instruction, right? Instruction definition and encodings. Definitely, those are elements. But instruction sequencing model is an element, and we've covered this earlier. Control flow versus data flow. How do you sequence between instructions, right? And there are many trade-offs, as we've discussed last time. The second is instruction processing style, and you'll have a homework question on this. This specifies the number of operands an instruction operates on and how it does so. Have you guys heard about stack machines? Yes? You covered it in 213? Yes? Okay, so you know what it is. So you'll have an exercise. But basically, what this means is, traditionally we've had 0, 1, 2, or 3 address machines. 0 address machine means that the instruction, the operate instruction, specifies only 0 operands. Which means that the operands are implicit. And that's a stack machine. Basically, in a stack machine, an operate instruction operates on the top elements of the stack. That's it. You don't need to specify which register or which memory location the operands are in. If you have 1 address machine, this is an accumulator machine, you can actually specify what to add to the accumulator, for example. 2 address machine, now you have 2 operands. Your add, let's say, it has 2 operands. If you're adding 2 things, let me actually use the board now, if I can. And I'll try to stick to this side so that it can be recorded. So a 2 address machine, you have add destination register, source register, destination register, which means that one of the operands is always the destination. Source and destination are really the same, right? So, which means that you actually overwrite the source. Now, the upside of this is it's compact encoding, right? And 3 address machine is the most powerful, if you will, most powerful in terms of expressiveness, or 3 operand machine. Now, that's what we've seen earlier, right? With LC3B, for example, you have 2 different source register specifiers that could be different from the destination register. So you have 3 addresses you can operate on. Here you have 2 addresses. In stack machine, you have 0 address. You just do add. And in an accumulator machine, you have 1 address, add to the accumulator. Right? Or actually add some register or some location to the accumulator, add A, let's say. Okay? So you'll have a question in your homework to look at these different trade-offs. I'll give you some of them, but if you have, as the number of addresses increases, you have larger operate instructions, right? Because you really need to encode the IDs or locations of these different operands. With a stack machine, you just need to say add. You just need an opcode. That's it. But the downside with a stack machine is you may have more executed operations, right? And maybe it may be hard to express these things because you always operate on the top of stack. Whenever you need to operate, you cannot just access any arbitrary value. That makes it tough to program these machines. Code size versus execution time versus on-chip memory space is a trade-off also. Right? Your code size might be really small with the stack machine, but you may need more operations. Your instruction size can be really small with the stack machine. Right? But again, you may need more operations. Again, your instruction size here may be small, smaller than a 3-address machine. A 2-address machine has an instruction, at least an operate instruction size that's smaller than a 3-address machine. But you may need more operations because a 2-address machine always clobbers the destination, right? What if you needed the source value later on? Well, what do you do in that case? Yeah, you move it before you actually clobber the destination, which means that you need an additional move operation to keep it. That's why your code size increases. Okay, and on-chip memory space as well. Like what is that trade-off? So hopefully you'll see that a little bit. But let me give you an example of the stack machine. The upside is small instruction sizes, as I said. No operands are needed for the operate instructions. And remember that this is really for the operate instructions. You still need loads and stores, or pushes and pops. This leads to simpler logic and compact code. Right? This also has the advantage that you can have efficient procedure calls, right? You can have all parameters on the stack and operate on them. There's no additional cycles needed for parameter passing. The downside of this is actually a lot of the early calculators were stack machines. Now you could express computations that way. So the downside is computations that are not easily expressible with a postfix notation are difficult to map to stack machines. Basically, you need to think from the mind of a stack, right? The operations that you need to do first need to be at the top of the stack. Right? Does that make sense? So if you're, actually, I think I have an example next. Have you programmed these old calculators with stack machines? You have? How many of you have? Was this part of a course? Which course? 341. Oh, 341. I guess who has taken 341 here? Who hasn't? I guess the rest, huh? Okay, so those of you who have taken 341 know the stack machines, huh? I guess who doesn't know is another question, but I want to ask that. Yeah. Yeah, so you know, if you've taken 341, you know that. It's a simple concept. But the downside is basically you cannot perform operations on many values at the same time. You're limited to only top n values on the stack at the same time, which means that it's not flexible. So let's take a look at this. Actually, Phil Koopman, who's a professor in the department, has worked on stack computers for a long time. And this is his book from 1989. And his book was titled Stack Computers, The New Wave. So computers have evolved quite a bit over time, right? And you can take a look at his book, actually. You can find, this is a picture from his book, section 3.2. If you want to learn about stack computers, you can take a look at it. It has a lot of information about stack computers, which is very interesting. But basically, if you look at this, you have a data stack. Let's concern ourselves with the data stack over here. Return stack is really for procedure calls. But operate instructions take values from the data stack and actually, the top of stack is buffered here, apparently. Buffer the top of stack over here and get the data from the next top of stack and just operate on the top two elements in the stack. Let me give you an example. Again, this is from that book. Initially, you have an empty stack. If you want to do some computation, you push 98 to the stack. This is a push 98. That takes the value from a memory location, pushes it on top of the stack. And stack is a hardware stack over here, which is different from memory over here. You could just have the stack itself, but it's more general purpose if you have memory and load the stack with values over there. You load the top of stack with 98. You load, you do a push 12, which loads from memory to the top of the stack. And these could be addresses, actually. You could make it more expressive. This is just an example. And then you push 45. This is what you get. These are the three values, and this is the top of stack. Now, if you do add, if you just say add, it adds the top two values in the stack and pushes the result back on the stack. It basically replaces the top of stack with the addition of the top two values. That's what you get. Now, if you have a multiply, it multiplies the top two values in the stack and pushes the result back on the stack. Right? This is basically what a calculator used to do a long time ago, a stack-based calculator. It's fun, right? But now you need to express your computation such that it's in this notation, right? You don't want to do the multiply before the add. OK? I'm going through this quickly because it's an easy concept, and you'll have a homework question, even if you do not know this. Any questions? OK, great. I can go quicker? No? You can stop me if I go too quickly. OK, there are other examples. PDP, remember the program data processor that I mentioned that actually made Digital Equipment Corporation a really strong corporation in the market. It was a two-address machine, just like x86. Actually, x86 is a two-address machine, too. So for PDP-11 add, for example, had a 4-bit opcode and two 6-bit operand specifiers. 6-bit because you had 64 registers. Well, why was it a two-address machine? Because they wanted to keep the instructions 16 bits. That's the main reason. And they still want to have that many registers. And code size was very important at that time, to keep the code small as possible. The disadvantage of this we've already covered. One source operand is always clobbered with the result of the instruction, right? You cannot have the source you cannot have the destination register different from both of the source operands. Well, we already answered this question, right? How do you ensure you preserve the old value of the destination register? You basically move it to some other place, maybe to memory. OK, x86, is a 2-address machine, actually. In fact, we'll look at memory-to-memory and load-store machines in a little bit. x86, you can specify operations from one memory location to another memory location without going through the registers. You can basically increment a memory location. You can copy one memory location to another memory location. Well, I guess that's you can copy multiple memory locations to multiple memory locations too. We'll see that. In fact, that will be another homework question of yours. Alpha is a 3-address machine. It's load store. What about MIPS and ARM? ARM is 3-address and MIPS is 3-address also, right? Okay. Okay. So instruction, remember we've talked about what an instruction looks like. It has an opcode, for sure, and it's operand specifiers, right? One key thing is, how do you actually obtain the operand? And this has a name called the addressing mode. How do you figure out where your operand is for the operate instruction? Or for any kind of instruction, actually. An addressing mode specifies how to obtain the operands. And there are different addressing modes in an ISA. So here, you're addressing a register, really, right? This is called the register addressing mode. The operand is in a register, and you specify the register ID. But there can be many, many addressing modes, and we'll see that in a little bit. In fact, I don't remember. How many addressing modes are you going to are we having the students implement this time with ARM? Only 2? Oh, we were nice to you. ARM actually has many addressing modes. Not as many as VAX or x86, but you'll get to know 2. Data types. Let me cover data types first. You probably covered this in 213, but data types is representation of information for which there are operate instructions that operate on that representation. For example, integer, floating point, character, binary, decimal, or binary coded decimal. These are all different data types. Integer means that the data value in the register is an integer, and when you add the 2 registers, you get an integer result. They don't have to be integers, right? They can be in floating point format or fixed point format. They could be characters, right? You can add 2 characters and define operations on characters. They could be binary or decimal values or binary coded decimal values. But there could be more complex data types also. These are simple data types, relatively. You could have a doubly linked list as a data type in your ISA, right? You can have an instruction that says insert into a doubly linked list. And in fact, there were ISAs like VAX that had that instruction. Q instruction, insert Q, remove Q instructions. They operate on a doubly linked list instruction that basically looked at a bit vector and find the first bit that was set going from left to right. Does that make sense? So in this case, bit vector is a data type, right? And you would like to find the first bit that is set. Now this is actually, it turns out this is actually useful for a lot of resource allocation decisions that you make in the operating system. If you have a resource, let's say you have 32 instances of a resource, and you want to figure out if something is available. You want to figure out the first resource that's available. Available is represented as a 1 in a bit vector, in a 1 hot bit vector. Well, not 1 hot, but in a bit vector. And you want to first find the first resource that's available. This is nice, right? Find first instruction. Instead of having many instructions to figure that out, you have one instruction that figures it out for you. Q, well, I guess in VAX it was double linked list. It was called Q, but it was really a double linked list. String operations, which you will become very familiar with. Stack could be another data type. In stack computers, actually, it's a fundamental data type, right? But it could be, actually, you can imagine and you could make it anything a data type. Right? Pointer could be a data type. In today's architectures, you don't have that, but pointer definitely could be a data type. And I'd recommend that you read this one tonight, the VAX Architecture Handbook. It's a beautiful book from 1977. You'll learn a lot. But first, do your lab. So in x86 also has many data types. It's very rich. It has a scan opcode that operates on character strings. It has push pop. So stack is a data type in x86. Strings are data types in x86. So let's back up a little. These are just examples, and you can read the ISA manuals to see different examples. So what is the benefit of having more or high-level data types in the ISA? Anybody can guess? Yes?
You could possibly create fast implementations of hardware.
That's right, exactly. And that's the benefit. You could support it, and your programs can run much faster. And in fact, you don't need as many instructions if you have an insert Q instruction, right? If you have a string copy instruction that does everything for you, you don't need to do everything with loads and stores to that. If you compare to when you didn't have that data type. What is the disadvantage? Yes?
Well, it's extra hardware cost and power, but also if you want to make a small change to the data structure, you can't do that because it's hardware, so that's wasted hardware.
That's right. So the first thing is extra hardware cost. Because you still need to support adds probably in addition, right? You have some fundamental primitive instructions, add, multiply, load. You can potentially support the data types with that. But now you're also adding these new instructions that you need to support, so that's the extra hardware cost. And if you actually burn the data type into hardware, you need to, the programmer, if it's not flexible enough, the programmer needs to use that. Otherwise, they won't use it. There are some data types in x86, for example, that are not used as much today. Binary coded decimal, for example. It's not used as much today. So basically, think compiler, programmer versus microarchitect here. That's another trade-off that we're making. If your data type is high level, and if it fits the programmer's needs, this is great, right? The compiler can just see a linked list and use the instructions, map the instructions very quickly. It doesn't need to generate all of those add, multiply, divide, whatever instructions that you need to. It doesn't need to do much translation, basically, to low-level instructions. But now microarchitect's life is harder. Right? Now microarchitect needs to support all of these instructions. And this ties into the concept of semantic gap. Have you ever heard of a semantic gap? No? OK. Basically, data types are coupled to the semantic level, or the complexity of instructions. Let me give you the example over here. We'll get back to this when we talk about complex versus simple instructions. But I'd like to give you an overview first. So the idea of semantic gap is you have this high-level language with some data types. And you have a program that's written in that high-level language. Eventually, the goal of the computer is to map it to control signals, right? And the idea of semantic gap is where your ISA is placed between the high-level language and the control signals. You can make the choice that your ISA is at the level of high-level language, right? You can execute only that language. Now your data types are exactly matching what the high-level language specifies. Or you could make the choice that your ISA is much lower over here, which means that your data types are very, very primitive. And the idea, the distance between the high-level language and the ISA is the semantic gap. Now, it's a fuzzy definition because how do you measure this thing, right? You cannot measure it. But we can think of it as being large semantic gap, which means that ISA is very low level, close to the control signals, or small semantic gap, which means the ISA is very high level. I would put, for example, to be a little bit more exemplary, I'll put x86 somewhere over here. It has a small semantic gap because it has these rich data types. And VAX probably a little bit higher in terms of the data types. It has these rich, even richer data types, doubly linked list, which are closer to high-level languages, right? Whereas maybe MIPS over here, right? Especially the initial MIPS. Initial MIPS had only the integer data type. It didn't even have the floating point. And they discovered that the floating point programs were actually running like a dog. So they added the floating point data type afterwards. So they actually increased the, they reduced the semantic gap as the ISA evolved. Well, you could think of an ISA that actually has control signals, right? It exposes everything in the processor, everything in the microarchitecture up, such that. So the difficulty over here is if your semantic gap is low, it's easier actually, assuming that the compiler can recognize the constructs well. It's easier for the compiler to generate code, right? It's easier for the programmer to go from here to here. if your semantic gap is actually high, large, it's harder for the compiler to go from the high-level language to closer to control signals. Right. Then you need to translate everything to smaller, primitive instructions. Okay, we'll get back to this when we talk about complex versus simple instructions. But it applies to data types. It applies to complex versus simple instructions. And these go hand in hand, right? If you have complex data types, you necessarily need complex instructions. Yes?
So to use the built-in hardware data structures, does that mean the programmer would have to know, like, specifically how to construct their W list, like a C program, for example?
So if the I guess if the ISA is right here, they need to. But if there's an extra step in the middle, the compiler can translate what the programmer constructs to the ISA's data structure. Right. So the compiler can bridge that gap. If you're programming directly into assembly, yes. But if you're programming at a little bit higher level language and translating into the ISA, then the compiler can do that. That's a good question, though. You can take a look at the VAX manual and see. OK. Intel 432. So early RISC, I already said that. Only integer data type was there. And then floating point was added. And then other things. Early RISC didn't have multiply instructions. We'll get back to that. Yes?
Actually, the control signals could be also variant. I mean, you could have only integer operations, but ISA supports floating point, for example. And with those like integer hardware, it emulates the floating point. That could be also variant, right?
That's right, yes. That's right. We'll get back to that. Now you're thinking about, so translation will change the trade-offs, and we'll get to that. So you could actually support other operations by adding another layer of indirection over here. That's good thinking. So Intel 432 was a very complex machine that had a lot of data types also, and you can take a look at that. Okay, we'll get back to that discussion. But other elements of the ISA, memory organization is a critical element, and this consists of many different things related to memory. You probably know address space and addressability, right? Address space is basically how many uniquely identifiable locations you have in memory. And addressability is how much data does each uniquely identifiable location store. These are different things. For example, you can have a byte addressable machine. Most ISAs are byte addressable. Like ARM is byte addressable, right? MIPS is byte addressable. In this case, the characters are 8 bits also. Right? And that's the reason you have byte addressability. Your characters are 8 bits, and you would like to get 8 bits. You could have a bit addressable machine too, right? Basically, do you know any ISAs that address every single bit in memory? When you do a load, it specifies a bit. Do you need that? Well, there was a machine actually, the Burroughs 1700. They could address every single bit in memory. Today, if you want to get a bit in a byte addressable machine, you need to read the byte and then extract that bit, right, with shifting and XORing. But Burroughs had this, and the reason they had it was because they wanted to emulate any kind of addressability. They designed this machine such that it could be a virtual machine. And you could actually design any kind of ISA on top of this. You could do any type of addressability. Anyway, you can take a look at the paper that describes it. You could actually have 64-bit addressable machine. In this case, your granularity of addressability is higher, right? 8 bytes. Some supercomputers actually had that because they operated on values that are as large as 64 bits. They didn't really need to address every single byte. So again, this shows how you can design the ISA, how you can tune the ISA to your design point, right? If you're running only supercomputer jobs with where elements are 64 bits, maybe this is a good design choice to make for that design point. First alpha, this is actually one of the potentially a mistake that the alpha did initially, but they corrected it quickly. First alpha was 32-bit addressable. So you could basically get what is usually called a word. Actually, I think in alpha it was double word, but I'm not sure. 4 bytes. You could address 4 bytes. You could not load a single byte from memory. And they've quickly figured out that actually it's a good idea to have a load byte and store byte operation. And they added that to the ISA. And load byte and store byte operations are very useful if you're doing graphics, right? Because your characters and pixels are 8 bits. They're not 32 bits usually. Okay. I guess I'll leave this to you. How do you add two 32-bit numbers with only byte addressability? These are some questions that you can think about on your own. And how do you add two 8-bit numbers with 32-bit addressability? The answers are simple, right? You just need to do some loading and shifting and masking, and you need additional instructions to be able to do that. So big endian versus little endian, how many of you know that? Know the distinction? A lot. How many of you don't? No? Don't be shy. It's okay, I want to see you. Okay. Which class did you learn in? 213, yeah, you should learn in 213. But we'll take a look at this. Basically, this in a big endian machine, the most significant byte is at the, let's see, I always get confused with this. Most significant byte is actually at the low byte, right? In a little endian machine, most significant byte is at the high byte.
So if you get confused, it's like big end first, right? Or little end first.
Oh, I see. Okay. I'm still confused. It's a notation, yes. But that's, I'll try to remember that. So support for virtual memory is another thing. So big endian versus little endian is a characteristic of the ISA, basically. x86 is little endian. I believe Spark was big endian, but I'm not sure. ARM is little endian, right? Oh, it can be either. You can change the mode. Okay. What is the default? Is there a default? No? I think the default is little. That's what I remember. But I mean, if you can change it, you can change the default too, right? Okay. Support for virtual memory, which we will cover, is another element of the ISA that's related to the memory organization. So if, let's see if, okay, this may be a good place to stop, actually. I'll give you some readings. If you want to dig deeper, if you want to learn about Burroughs 1700, this is a good paper. And if you really want to learn about a relatively complex machine, Intel 432 is a relatively complex machine. And this chapter actually talks about how it's designed. Actually, let me stop here for 3 minutes, and then we can continue. Is that good? Okay, 3 minutes. Oh, okay. The registers you have, and size of each register. But not all ISAs actually have registers. Why is it a good idea to have registers? We probably covered this before in 213. Memory is slow. That's good. So you want to keep fast storage closer to the processor, right? But why do you want to make it visible to the programmer or the compiler? Yes. Mm-hmm. So the compiler or the programmer can figure out what are those values that you really need, which values have a lot of locality, and keep them in this fast storage, right? So basically, we're exploiting the principle of data locality. Right? You're working on some set of values very frequently. You're reusing them quickly. And a lot of programs exhibit this characteristic. They load a value and they work on it a little bit, and then they're done with it. And registers exploit that. They exploit the fact that a recently produced or accessed value is likely to be used more than once. This is temporal locality. Now, this is the same thing caches exploit, right? You could think of registers as a cache that the programmer controls. Right? It's a very special memory space that the programmer or the compiler can control. It's essentially for the same purpose, to keep frequently used values closer to the processor such that your program can run fast. Basically, storing that value in a register eliminates the need to go through memory each time that value is needed. Okay. So basically, registers are programmer visible state, but you can do the same thing with caching, right? In a way that's invisible to the programmer. The reason we have registers as compilers can analyze this and keep them in a separate memory space. So register address space is different from the memory address space. You don't have to have registers. You can have a machine that looks like this to the programmer. You can have a program counter, memory address of the current instruction, and memory locations, right? This could be your only architectural state, and maybe some machine registers. Now, this could run slow, but you could also say that I add a cache, which we will see a lot later on. You add a cache, and you can speed up how it runs. But many ISAs actually specify these registers that have special names, as opposed to memory addresses, that could potentially be general or special purpose that the programmer or the compiler can use to maximize performance. And the hope is that the programmer and the compiler can do a better job managing this than the hardware. Okay, and instructions specify how to transform the values of the programmer visible state. Okay, while we're at the programmer visible state, so that's the purpose of registers. There's also programmer invisible state. This is called the microarchitectural state, right? Programmer cannot access this directly. Cache state or pipeline registers, normally they're not accessible directly. So as a result, they're part of the microarchitecture. But let's get back to the register architecture. So registers have not always been general purpose registers. For example, we've seen, well, it's gone now, but we've seen destination register, source register, specifiers over here, right? In an accumulator architecture, you just have an accumulator, right? In a stack machine, actually, you don't have registers, right? In an accumulator architecture, you have one register, that's the accumulator. And later, machines evolved by adding these address registers. So address registers is a very special purpose. The goal was to actually load from memory. They just kept addresses to load a value from the address register from the address specified by the address register into the accumulator. And eventually, they actually supported arithmetic on addresses. So over time, the register architecture evolved to be more general purpose. So for example, in IBM 36091, I believe there were registers that were specified. It wasn't an accumulator machine. It had some registers that operate on data, that store data values. And to access memory, you needed to use a different set of registers. Those are address registers. So those were special purpose. This makes it easier to design, because but you now have different instructions to operate on them. But over time, things became more general purpose so that it was easier to program. And all registers became good for all purposes. Right? For example, in ARM, you have 32 registers, right? Is that correct? Or is it 64?
Sort of 32.
What do you mean sort of 32?
Access 15 or 16 at a time.
Okay. Oh, that's, yeah. Yeah, ARM is not the perfect RISC ISA. That's why over here I said common for RISC. In alpha, which is beautiful, you have 32 registers. I guess in x86 today you have, is that 16 registers? It used to be 8 for a long time. Now it's 16 registers, right? Or have they increased it to 32? Probably not. That's tougher to do if your instructions don't specify enough bits, right? Okay. In Intel IA64, it was 128 registers. It's a very large number of registers. Okay. Okay. You'll get familiar with this more and more as you implement your processor. But there are also instruction classes, and ISA specifies instruction classes also. Operated instructions. I'll go through these relatively quickly. This is part of your reading too. Operated instructions process data. They could be arithmetic or logical operations. Basically, they fetch their operands, they compute the result, and store the result. And the control flow is implicitly sequential in a sequential ISA between them. There are also data movement instructions that move data between memory, registers, and I/O devices. And again, the control flow is sequential between them and between operated instructions. Control flow instructions change the sequence of instructions that are executed. And these usually have different formats. If you remember from the previous, actually I think it was the alpha picture that showed the different formats. These had different formats. Okay, we briefly alluded to this, but an important element of the ISA is whether it supports load-store operations into registers, or it also supports memory-to-memory operations. This is different from whether or not you have registers. You may have registers and only be a load-store ISA, you never support operations between two memory locations. Or you could have registers but also support memory-to-memory operations. Right? In a load store architecture, operate instructions operate only on registers. MIPS, ARM, and many RISC ISAs are like that. There's no way you can operate on a value without putting into a register first. In a memory-to-memory architecture, operate instructions can operate on memory locations as well, in addition to operating on registers. x86 is an example. You could increment a memory location. If you want to increment a memory location in MIPS or ARM, you first need to load that memory location to a register, the data value, and increment it and store it back. So you see the trade-off, right? If you have memory-memory architecture, you don't need to clobber a register if you're not going to reuse it. If all you're doing is incrementing or zeroing, initializing a huge amount of memory, you never need to clobber the registers. Right? And you're never going to use that memory for a long time. Then you don't need to clobber the registers. That's the upside of a memory-memory architecture. The other upside is you don't need as many instructions, right? Well, the downside is now hardware complexity again, right? The hardware needs to support not only load store operations, but also these memory-to-memory operations. Again, it makes life easier, perhaps, for the programmer, but it makes life harder for the microarchitect. OK, and we'll see examples of this. In fact, in your homework, you'll do some memory-to-memory operations. We'll get to this soon. So addressing modes, let's return to addressing modes because they determine how you actually obtain your operands. In a load store machine, your addressing modes for the operate instructions do not need to specify memory addresses. Whereas in a memory-memory architecture, your addressing modes for the operate instructions need to specify memory addresses, right? An addressing mode specifies how to obtain the operands. Are you guys familiar with addressing modes? OK, I'll keep going quickly then, unless somebody shouts and says, I don't know this. OK, absolute addressing mode, basically, this is the immediate value. In this case, the operand is within the instruction. It's specified within the instruction. It's also called the immediate addressing mode. Register indirect, basically, the operand is specified as a register ID, and it's in the register file. This is displacement-based or based addressing mode. The different architectures call it differently. But basically, you take the value in the register, and you add an offset to it, and use that as address. Indexed, you can basically add multiple registers, right? Now it becomes more complex as you go down this way. You can have memory indirect. You can take the value in the register identifier, access the register file. You take that value and access memory. So basically, what's in the register is really a pointer to memory. And this could be useful if you're doing pointer accesses, right? OK, auto increment and decrement. OK, we'll take a look at it, actually. Do you guys know auto increment and decrement? Yes? How many of you do? Have you ever used it? Yes?
Does the ARM do that when you're like storing multiple or something? It's for like supporting stacks.
Or yeah, it could be for supporting stack. It could be for supporting array accesses. If you're, for example, loading an array in a consecutive manner, what auto increment does is, well, I guess we'll get to that in the next slide. But what auto increment does is, for an instruction, if you do load with register 5 as the base address, and if it's a load with auto increment, what the load does is uses this as an address to memory, gets the value, and increments R5 by some value, by 1, let's say. Now this enables, if you're going through memory and sequentially loading, what you can do is you can load the first value, and now you have the next address, the address of the next value in register 5. So you don't need to do an explicit add operation to calculate the address. Right? That's the upside of it. OK, so this is basically these addressing modes is another example of the programmer versus microarchitect trade-off that we're going to cover a lot in this course. Having more addressing modes is good for the, well, could be good for the programmer as long as the programmer can use it. Right? Basically, it enables better mapping of high-level constructs to the machine. And I'll give you specific examples of this. Some accesses are better expressed with a different mode. As a result, you get reduced number of instructions and code size. This is one example. If you're actually going through an array and adding, let's say you're incrementing an array, and let's say you have load store architecture. With an auto increment addressing mode, all you need to do is have a loop where you load from this array. This is the R5 initially points to the base of the array, and you have a load that loads the first element, and automatically R5 is incremented, so now R5 points to the next one. Now you can have an increment instruction. Well, I guess load needs to specify the destination register too, right? That's a good idea. R2, increment R2, and then you need to, I guess, do something with it, and then you just need to branch, right? Okay. Anyway, I didn't do a good job over here, but hopefully you got it. Any ideas? Should I go through this more? Okay. I'll let you figure it out. But think array accesses in an auto increment mode. If you're doing pointer chasing, indirection is helpful. So this mode over here that does indirection is helpful. Basically, you go to a location, get the address, and treat that as a pointer, and go to the memory location again. And you could actually support other accesses. I'll give you an example from x86 soon. The disadvantage of this is now you have more work for the compiler, right? Now the compiler needs to figure out the best addressing mode for, well, I guess the addressing modes, having more addressing modes could be good for the compiler if it can map the address, map the data structure nicely to the addressing mode. If it cannot, it could be more work for the compiler. Definitely supporting more addressing modes is bad for the microarchitect. Right? The microarchitect now needs to support all of these different addressing modes. It enables flexibility to the software. That's the upside. Now the software, if it can map things to the right addressing mode, you can run fast. Right? And your code size can be smaller. If it cannot, then there's a problem. But in most cases, you can actually map. Array accesses, for example, or pointer chasing, you can map. So this brings me to ISA orthogonality, which is actually relevant to addressing modes. In orthogonal ISA, do you guys know what an orthogonal ISA is? Okay. This is just a definition. Somebody made up the term orthogonal ISA. But it's basically all addressing modes can be used with all instruction types. Addressing modes are orthogonal to the instruction types. An example is VAX, actually. This is, I told you that this is a very complicated ISA, right? It actually has 13 addressing modes. That's a lot. If you're interested, you can take a look at the ISA manual. I would bring it up, but I would like to cover more today so that we can get into the more exciting things in the future. And it has 300 opcodes. And it has integer and FP formats. Now think about orthogonality. You can have many different ways of forming an instruction. Right? You can multiply this, and that's what you would get. That's a lot. And VAX was an orthogonal ISA. I guess having orthogonality, who is that good for? Who is that bad for? If you have an orthogonal ISA, is it good for the compiler? It is good, right? Because the compiler doesn't need to special case anything. It can use any instruction with any addressing mode. These are totally orthogonal. Otherwise, the compiler, you need to specify the compiler, this add instruction can use only this addressing mode, right? Well, if you have orthogonal ISA, it's bad for the microarchitect again. Right? Now the microarchitect really needs to support every single addressing mode with every single instruction. And that's just additional hardware. I guess here's one question for you. This is the LC3B ISA. And these are some of the instructions. Is it orthogonal? I know you haven't looked at the specification, but maybe by just looking at this, you can tell me. You say no. Why not?
Well, because sometimes it has this 8-bit. Sometimes it has the, what was that called? Bit steering.
That's right.
Sometimes it doesn't. So you can't use all.
That's right. Yes. So basically, you cannot use all addressing modes with all instructions. Right. Every single instruction. You can look at this by just looking at the store instruction over here and add instruction over here, as you mentioned. So store instruction, for example, has a base plus offset addressing mode. I know you haven't looked at the ISA manual, but that's what this says. You determine base plus offset as your address. But for other instructions, you don't have base plus offset addressing mode. Right? So you cannot use every addressing mode with every instruction. So it's not orthogonal. This is one example with add. These are the addressing modes. In an add, your addressing modes can be a register addressing mode, or everything is registers, or immediate addressing mode, right? And that's the A-bit determines that. Whereas JSR, jump to subroutine, you have two addressing modes that are totally different. One is this one, which is PC plus offset. You basically jump to a location that's specified by the program counter plus this sign extended left shifted offset. Or you can change the program counter to a base register. It's a jump to subroutine instruction. You're going to implement something like this for ARM. Make sense? So this doesn't use an immediate addressing mode, for example. There's no addressing mode over here that says, take some immediate and just jump to it. You don't have that. Whereas if it was like add, you would have had that, right? OK. So how to interface with I/O devices is another element of an ISA. And we're not going to cover that as much in this course, but this is also important. How do you do I/O? Input, output. You could have special I/O instructions. For example, in x86, you have in and out instructions that deal with ports of the chip directly. Or you could do memory mapped I/O, which most processors today do. Right? You could map a region of memory to the I/O devices and treat the I/O device just like memory. You do loads and stores to the I/O device. And we will see this in the LC3B ISA a little bit. Trade-offs, well, which one's more general purpose? This one's a little bit more general purpose, right? Because you treat everything as memory. It would be nice. We briefly talked about treating storage as memory earlier. It would be nice if you can actually do that for I/O devices too. In this case, your keyboard is your memory, really. Except it's a special location in memory, right? If you're getting data from your keyboard, the keyboard places data into memory. I guess if you're writing data into your keyboard, that may not work. Your monitor, that'll work, right? OK, so there are some other elements of the ISA, and these are all specified in the ISA manual. Privileged modes, basically user versus supervisor, who can execute what instructions, what is permissible in the mode, how do you change the mode. Exception and interrupt handling, we'll talk about this, especially in terms of supporting exceptions. Basically, what procedure is followed when something goes wrong with an instruction. For example, you're doing divide by 0. You figure, the processor figures out that the second operand of the divide is 0. What happens at that point? What procedure is followed when an external device requests the processor? This is an exception. This is an interrupt. Interrupt is always external to the program that's currently running. And are you guys familiar with vectored versus non-vectored interrupts? How many of you are not? OK, I'll briefly cover that. But basically, when an interrupt happens, the interrupting device can specify a vector, which is used to figure out, which is used to directly index into the interrupt service routine to service that device. This is called a vectored interrupt. Basically, the interrupting device identifies itself with something called an interrupt vector. Now, this is nice because now you can take that identification, that vector, and the processor can go into a location in memory and start executing code. Non-vectored interrupts is a little bit different. Basically, the processor only knows whether you have an interrupt or not. It doesn't know which device is interrupting. There's no information. So early MIPS actually had non-vectored interrupts, and then they moved to vectored interrupts. This is simple. This is a little bit simpler, right? Non-vectored interrupts, because the devices don't need to identify themselves. Now, how do you figure out which device is interrupting if you have non-vectored interrupts? Is it the keyboard? Is it the monitor? Is it something else? Right? Is it the disk? Any ideas? Yes? Exactly. You check all of them, which is painful, right? You basically go through each device. The processor, when it gets an interrupt, it goes through each device and says, did you interrupt me? Did you interrupt me? Did you interrupt me? Well, vectored interrupts are much nicer, basically. This is more old style. It's simpler, perhaps, but it's, again, simple hardware, right? Hardware is simpler in this case. And that's why MIPS made that design choice early on, but then they retracted it. Virtual memory, we'll see that a lot later on. Basically, does each program have the illusion of the entire memory space or not? And virtual memory enables that. access protection, basically what kind of access protection modes there are. This is also specified by the ISA. We'll not talk about this as much, but we'll talk about it a little bit when we get to virtual memory. Okay, let's go back to complex versus simple instructions. I'd like to cover that in a little bit more detail because that's such an important part of the ISA. Let me treat it in a little bit more detail. Basically, a complex instruction means that the instruction does a lot of work. I know this is not a very concrete definition, but it's a lot of work compared to a simple instruction. Basically, it leads to many operations. Think about simple instruction being an add, and a complex instruction copy one string to another string. Right? There's no question that copy one string to another string is a lot of work compared to an add. Simple instruction, an instruction does small amount of work. It's a primitive using which complex instruction can be built. Insert into a doubly linked list, compute the FFT, string copy. These are all complex instructions. Compute a polynomial, which VAX actually had. They're all complex instructions, right? Simple instructions add, XOR, multiply. Okay. So what are the advantages of the complex instructions? We briefly covered that, right? Yeah.
Code size.
Code size, yes, that's a big advantage, right? If you can map to these, map your program to complex instructions, you have denser encoding, smaller code size, better memory utilization. You can save many, many things, right? You can save off-chip bandwidth, for example, when you're accessing to get your code. You can get better cache hit rate, better packing of instructions. So that's what denser encoding actually enables. And the compiler, hopefully, is simpler, right? Assuming you can do this mapping nicely between the high-level language and the complex instruction. So I guess I'll use this still because we'll get to semantic gap again. Basic complex instructions put the ISA closer to here. Well, let me put this again. High-level language, control signals. Life is easier for the compiler, assuming it can do this mapping. And that's the hope. There's no need to optimize small instructions as much. The hope is that the hardware is optimizing those the large instructions, right? The complex instructions. It's optimizing the string copy, for example. But these are disadvantages. Well, now you have larger chunks of work, right? Well, this could be bad because now compiler has less opportunity to optimize, right? Because it has these larger chunks of work, and it cannot reorder them as much, right? Whereas if the compiler is generating only adds, multiplies, divides, maybe it can reorder them. It can figure out which ones are independent, which ones are dependent. It can reorder such that you minimize the stalls, and we will see that with pipelining. The obvious disadvantage is it's more complex hardware, right? Now the hardware needs to support all of these complex instructions and the corresponding complex data types. Translation from a high level to control signals and optimization needs to be done by the hardware. So if your ISA is here, compiler needs to do this much work. Think about it that way. And hardware needs to do this much work. As opposed to if your ISA is here, in that case, your hardware's work is simpler. Compiler's work is a lot more. At least to get the same performance if you want to equalize something. So this leads to this trade-off that we discussed, right? The semantic gap. Where to place this ISA? Is it here? Is it here? If it's closer to a high-level language, we call that it's a small semantic gap. It's small, semantically closer to the high-level language, which necessitates having complex instructions and complex data types, or complex data types. If the ISA is closer to the control signals, you have a large semantic gap from the high-level language, which necessitates simple instructions. Right? And this is the key difference between RISC versus CISC machines. How many of you have heard of this, RISC versus CISC? How many of you have not? Well, you guys all know what this is. This is a fuzzy term, but RISC is reduced instruction set computer, CISC is complex instruction set computer. And they differ, first of all, in where they place the ISA. For example, a quicksort instruction would be CISC, right? Polynomial instruction could be CISC. Alpha had this. FP instructions, are they RISC or CISC? Now we're getting fuzzier. Well, initially, if you're yeah.
Well, I was going to say, like, I would consider it CISC if it was actually emulating that for several iterations of clock cycles. So through this kind of pipeline, I thought it would be RISC if it actually had FQ support like on the chip.
Mm-hmm. Yeah, that's a tough one to argue. You could argue that way. But let me give you an example. Initially, the philosophy of the RISC machines was keep the hardware as simple as possible, which means that your ISA should be at this level, right? Control signals, which means that I guess you shouldn't support any data types. But that's an extreme, actually. This was IBM, John Cox's concept of a CISC machine. He called it the open microcode engine. Basically, you have control signals exposed to the compiler, and you map the high-level language to the control signals. You still have a general-purpose processor. It's not reconfigurable computing. You have a general-purpose processor. You just generate the control signals, right? Does that make sense? You don't reconfigure the hardware. That's the difference. You still have a pipeline, for example, but you just generate the control signals for every single operation that you want to do. Now, this is great for the hardware, right? You just design the hardware and not optimize for anything, perhaps. So hopefully, the compiler will somehow do the control signals right. Now, that's RISC. That's the extreme case of RISC. CISC, extreme case of CISC is it's up here, right? The compiler does nothing. You just take the program and execute it. That's a tougher thing to do also. They're both very tough to do. Starting from this kind of philosophy, the earliest RISC architectures did not have FP, floating point instructions, because it's a complicated data type than integer. You can emulate it with integer operations. MIPS, for example, did not have a floating point instruction. But they figured out it was taking too long, way too long, to do floating point operations, so they added support for floating point in the ISA. So VAX index instruction is another CISC instruction. You can have array access with bounds checking. Actually, it's multi-dimensional array access. OK, so what are the trade-offs? I think I'll leave some of this to you, but simple compiler, complex hardware, versus complex compiler, simple hardware. That's the first trade-off, right? If the ISA is here, compiler is simple, because the distance is small. If the ISA is here, actually, the compiler doesn't exist, perhaps, right? If the ISA is, yes?
Is there a reason that we're ignoring the fact that it's very difficult? Like, once you get to high-level constructs, it's very difficult for the computer to recognize what you mean.
Yeah, that's right. So we're kind of ignoring that. That's right. That's true. We're kind of ignoring that. You need to do that somehow. But the hope is that somehow you can express it, maybe through a translation layer. You don't do it dynamically, but you write the high-level language and you translate it quickly. Okay? But that's a good point. I mean, there are some assumptions that I'm making here. So that's the fundamental trade-off. But you can actually break this trade-off. Well, let me actually first cover this. I'll get back to this translation. You can actually change that trade-off. So burden of backwards compatibility. If you actually have lots of complex instructions, you have to support them, right? As you add more instructions, you need to support more instructions. Whereas if you have only primitive instructions, you only support that set of primitives. That's why x86 has a lot of instructions today, because it's added many, many instructions, many, many data types over time. So backward compatibility burden is worse with CISC architectures. Performance, well, performance is a tougher one. Is the performance of a RISC machine better than the performance of a CISC machine? Who says RISC is better? Simple instructions. Who says that is better? Who says CISC is better? Nobody wants to take a stance here. I guess, is it because of this question mark here? Who says it depends? That's good. It depends is the right answer here, actually. OK, let me give you the historical context. Historically, CISC architectures have been dominant. VAX, for example, is the mother of all CISC architectures, probably. And I'd encourage you to read the manual today if you want to learn more about it. But and initially, RISC architecture was motivated by the hypothesis that an architecture with simple instructions would be much higher performance than the VAX architecture because VAX architecture was tough to design, tough to optimize performance. And one of the proponents of the RISC architecture looked at an example instruction, a very complex instruction, the index instruction that I told you about. Basically, you could do multidimensional array access in an instruction with bounds checking. And they compiled a program using these instructions on VAX and measured its performance. And they also mapped these instructions, the same program, the high-level program, into simpler instructions in VAX and measured its performance. And they saw that if they used the index instruction, it took much longer to execute the program compared to if they used the simpler instructions, even though the simpler instruction had a much bigger code size. So this was the argument for, simple instructions. Using simple instruction on the VAX itself performs better than using complex instructions for the same program. That was the argument for RISC initially. Well, that's one of the supporting arguments. Now that was true, actually. Why was that true? Because VAX index instruction, the hardware designer didn't really optimize it. They really had this instruction, and they converted it internally to RISC operations. And they didn't really optimize this instruction. As a result, it performed much slower. But on the other hand, you could optimize that instruction, and you could perform much faster. Right? For example, with auto-increment addressing mode, you could argue that this is more CISC than RISC, having more addressing modes. You don't need to calculate the address, and in many cases, using addressing modes, higher level addressing modes wins in terms of performance. So basically, this really depends on where you spend, who spends more time optimizing. If you actually optimize your complex instructions, that could be a win. In fact, later, Bob Colwell, who was the lead architect of Pentium 4, actually Pentium Pro. He was an architect in Pentium 4 too, but he was the lead architect of Pentium Pro, which is the first general-purpose out-of-order execution machine. He's a graduate of the PhD program here at ECE. And his thesis was on comparing RISC versus CISC in the 1980s. And he showed that if the hardware is optimized, complex instructions can outperform simple instructions. He did his thesis on Intel i432. And then he went on to build very simple machines with the VLIW architectures, very long instruction word architectures. I think his company was Multiflow, which didn't succeed very well. And then he went to Intel and built more complex architectures, Pentium Pro, which is perhaps the most lucrative computer architecture that was ever built. In fact, the Intel computers that you have today are based on the Pentium Pro architecture. They're not exactly the same, but the core microarchitecture is based on the Pentium Pro architecture. It's not based on the other architectures that Intel later designed or earlier designed. Anyway, that's just an example. So it really depends, basically. It depends on who optimizes what. Here, with complex instructions, you enable the hardware an opportunity to optimize. Right? Now the hardware has the ability, hardware designer has the ability to optimize a very complex thing. And they could do a better job, potentially, if they put effort into it. Now, the reason why VAX architects did not optimize the index instruction was because nobody was using it. And this is a chicken and the egg problem, right? If nobody's using it, you're not optimizing it. And if you're not optimizing it, nobody's ever going to use it. Right? Now, that's the interesting thing about it. That's where this becomes an art also. Again, it's very hard to, yeah.
So you were mentioning that in, this, like, they're very similar kind of those studies and stuff like that. But in have anything been more done recently with like the whole multiprocessor idea? And like, I'm just thinking right now about CISC and trying to be able to schedule stuff to like different processors and expecting the results back. And even something like pipelining or out-of-order execution. I feel like with CISC, if you run like several of those instructions, you could actually slow it down a lot more than RISC, just because the processor constantly like have to be waiting for that CISC instruction to go through.
So that's an excellent point. That's why I'll get back to this translation. Modern architectures actually translate those CISC instructions to smaller operations internally. In a sense, what we discuss is not going to matter as much. That's where I'm taking you a little bit. Okay.
Yeah,
Yes.
so playing off that, could it be said that there's been sort of a convergence between CISC to RISC, and still not really they're translating these CISC instructions to microinstructions?
Yeah. So that's right. That's what translation enables, actually. Because CISC has some benefits also. Well, I guess I'll get back to this, but maybe I'll discuss this. Basically, translation can change many of these trade-offs. if you have a translation layer over here, what you can do is you can have a high-level ISA that gets translated into programmer invisible ISA, right? After which things get executed, right? And this is the translation, if you will. There are benefits to the RISC architecture. There are benefits to simple instructions, right? Simple instructions can actually, you can optimize things better, potentially. It's simpler hardware also, right? You don't need to, you just need to define a base set of instructions and you just optimize that. Whereas CISC hardware is much harder to design, especially if you want to optimize those instructions, right? So what people have done is to have a CISC ISA and translate it internally to a RISC ISA. ISA may be too strong over here, but programmer invisible set of instructions. And this is called actually micro operations in Intel terminology. Now, and this could be very similar to simple instructions, right? For example, if you have a CISC ISA and if you have a string move or string copy, which I'll have in the next slide, you can translate it to a set of load, store, multiply, add, branch, right? And you keep doing that. It's a trade-off, right? You've added a layer of indirection, which is this translation layer. Now the question is, who does this translation? Does the hardware do this translation? Or does the software do this translation? And we've seen actually both cases. In modern processors, modern x86 processors, the programmer visible ISA is CISC, x86, and the hardware, when it decodes a CISC instruction, a complex instruction, it breaks it down to simpler instructions. And the back end of the pipeline is optimized for those simpler instructions. So the back end is very similar to a RISC engine. But now you get the benefit of having a CISC ISA at the top. You get the code size benefits, for example. You get the compilation is less of an issue. Initially, actually, CISC ISAs were developed because compilers were not good at optimizing code. In the 1950s, 60s, compiler technology, software technology was not as advanced. So people, it was very difficult for the compiler to generate code that performed well at the low level, at the primitive instruction level. So this breaks the trade-off. This is really nice, right? This translation layer. So this is done by the x86 decoder in many architectures, many microprocessors that implement the x86 architecture. Now people are doing it in software also. Now software has a little bit more overhead, of course, right? Do you guys remember a company called Transmeta? Maybe remember is the wrong word, but do you guys know of a company? Yeah, one person. Only one? Yeah, I cannot be that old. So Transmeta, which was a competitor to Intel at the time, in the late 1990s and until early 2000s, what they did was their goal was to actually execute x86 programs, run all of the software that was written for x86 with a very simple processor. And their idea was they had this software layer that is proprietary, which they called the code morphing software. They took x86 assembly code, they translated it as part of this part of their firmware. They translated it into a VLIW ISA, very long instruction word. Basically, what the software did was translate. In addition to translating operations, complex operations to simple operations, it also found out what operations could be executed independently, and packed independent operations in a single instruction, such that you could get much higher performance. And their goal was that they could figure out a lot of independent operations this way. And well, it was tough for them to survive in the market. But the downside of this is doing this in software is it's a lot of overhead, right? Now you need to do this translation in software. Yes.
Is that similar to like what Apple did when they switched from PowerPC to Intel? That they had the Rosetta layer that translated the PowerPC code to x86.
That's right. I believe they did it purely in software, right? It's like a virtual machine. Actually, the virtual machine has the same principle, right? You could call this code morphing software a virtual machine. You're translating from one ISA to another ISA. That's right. That's very similar to what Apple did. There were other efforts also that translated other architectures to other architectures. Maybe ideally you want to define, if you want to execute all of the ISAs, you translate. You have a huge software that translates any ISA to your own internal ISA, right? That way you can run any program in the world. That may be tough. So this was a tough proposition for Transmeta, but this shows that you can actually break the trade-offs. You can make the hardware really simple while having a complex ISA, right? Because you have this additional layer of indirection. That additional layer of indirection can enable you to change the trade-off space quite a bit. That's the beauty of computer architecture. Actually, indirection is employed in many places in computer systems, right? Computer engineering. Okay, let me give you one example, and we're going to wrap up. So x86 has small semantic gap. An instruction, for example, operates on a string. You can move one string of arbitrary length to another location. You can compare two strings. Isn't that nice? And this is enabled by the ability to specify repeated execution of an instruction in the ISA. So using a prefix called the repeat prefix. For example, you have a repeat moveS instruction. Instruction opcode is moveS, move string, but you prefix it. Prefix is kind of a part of the instruction that specifies whether or not you should repeat this instruction. Do it repeatedly. The instruction is only 2 bytes, actually. You have a repeat prefix byte and a moveS opcode byte, these two, which is really simple, right? Well, simple in terms of decoding. You have implicit source and destination registers pointing to the two strings. ESI, source pointer to the source string. That's the memory that contains the memory location to the beginning of the source string. EDI points to the beginning of the destination string. And you have an implicit count register that specifies how long the string is, how many elements you need to copy. That's it, ECX. And that's your instruction. And this is how it operates. This is from the x86. And this is not the complete thing. This has a lot of abstractions away. But the x86 has all of these clues. Your address size could be 16. Your address size could be 32. If address is 16, you use CX for count register, blah, blah. I'll just go over here. But basically, you can use ECX for your count register. And this is what the instruction does. While count register is not equal to 0, you copy from the source string. Let's see. Well, this is it. Oh, there you go. Basically, this is what you do. And you can check whether you're moving a byte, word, double word, or quad word. But let's pick one of these. You basically, where do you actually do the move? Oh, there you go. The destination source, right? The source goes to the destination. That's where you do the copy. And then you increment the pointers. You basically go to the next location in the string. That's the idea. And this is a complex instruction because you can do it repeatedly, right? ECX can take any value. ECX is a 32-bit register. And you could, I assume, ECX could be 2 to the 32 at most. Which means that you can copy a string of 4 billion bytes to another string of 4 billion bytes, yes.
This doesn't prevent against wraparound, right? So
no.
Start at the high address and the count is greater than what you can go. Like it'll just go back down to 0.
Oh, there might be an exceptional condition that's specified in the x86 ISA. I don't know. That's the answer. But you can take a look at the instruction specification and see that. So this is a very complex instruction. And one of your homework questions is to figure out how many instructions does this take in ARM. I don't know if we asked the MIPS also, but I think we asked only ARM, right? It used to be a MIPS question. Now it's an ARM question. But hopefully you'll have fun with it. But think about how do you implement this in x86. So what is done in x86 today is actually repeat moveS is specified over here, and there's a hardware translation layer that goes into a microcode engine that basically iterates through a loop that issues these micro operations. Very similar to what you will write in your code. And the hardware does that. OK, I think let's stop here. And we won't have class on Monday because it's the MLK day, but I'll see you on Wednesday. Have a good weekend. And hopefully you get started on the assignments quickly.